standard enthalpy of formation is another useful way of you can solve problems with it and calculate heats of reaction, but it also is just kind of useful in understanding what's really happening with these reactions in terms of energy. Okay, so let's define it. So heat of formation, it's the heat required to form 1 mole of a substance at standard state from reference form elements. So standard state we define, and notice this is different than STP for gases because it's 25 degrees C. This is kind of room conditions. The reference form element in general is the most stable form of an element at this standard state. There is one exception, and ions in solution are actually sometimes more stable than like the solid that's the most stable, but anyway, this is a good way to think about it. If we're not looking at ions in solution, it's the most stable form that's possible. And you guys should know that for some elements, being diatomic is the most stable. So we know that those are the reference forms of those elements. Okay, and the reference form, so like oxygen, O2, that's a gas, its heat of formation, so this is what this means, formation, is 0. And that's true for all of the reference forms. Their heats of formation are considered 0. By the way, this little degree sign has to do with it being at standard state. Sometimes we leave that off and it's just kind of understood, but that's true. And then also just, so this is kind of like our floor. This is how thermodynamically we decided where 0 was, and then we'll compare everything else to that. Okay, so this is the standard enthalpy of formation. Of course, we call it the heat of formation a lot as well. Just like we do heat of reaction instead of standard enthalpy of reaction. Okay, carbon's kind of different because it has an allotrope. An allotrope is basically a crystal structure that is most stable. And so for carbon, graphite is the reference form of that element. And so because that is the reference form for carbon, its heat of formation is defined as 0. If you consider the reaction to take this carbon, this is the reference form, and make diamond, this takes some energy. This is for the reaction. It's 1.9 kilojoules. So the heat of formation for diamond is 1.9 kilojoules. This reaction, I'm going to really emphasize this reaction because I do sometimes ask about this on tests because it's key. This reaction is the reaction that defines heat of reaction. The heat of reaction is the energy, the delta H, for the reaction where you take the reference form and go to the one you're interested in. So that's why this is the heat of formation of diamond. It's based on that reaction. Heat of formation will be in kilojoules per mole. And this is how I like to think about it. It makes sense. You can think of heat of formation as how much energy a substance contains. Remember that enthalpy, or internal heat, is not hot. This is not how hot these are. This is how much the substance contains as a chemical potential energy. And so heat of formation is kind of like we're going to get to assign a number. We'll have a number for each different substance, and we can compare those to see what's happening in a chemical reaction. One way to say this is that something like gasoline, it would have a high heat of formation because a lot of energy is stored in it. Okay, so graphically, we can look at, I'm just like going back because I think maybe on your slides I had added a table in here. I'm not sure if it's on yours, but basically these numbers for heats of formation, you can look this up on a table. And every chemistry book has the table in the back, and to determine the amounts of heat in things. Okay, then I wanted to show you, like, graphically what's happening, or how this works. This, to me, this visual kind of makes it more clear what is going on. So I put carbon graphite here down at the bottom because its heat of formation is 0. And this is kind of the reaction I did. What if I took, this is energy diagram, carbon's down here at 0, and diamond has more energy stored in it, and this distance, this change, is the change in enthalpy to get to the diamond. So it's an endothermic reaction, and that is defined as the heat of formation for diamond. It's the amount of energy to make diamond from the reference form. Imagine a really unstable type of carbon. That would be carbon that's a gas. If I imagine carbon that's a gas, that's going to be it's going to take a lot of energy to go from graphite and heat it up and get it to be in the gaseous form. And so its heat of formation, the heat of formation for carbon as a gas, is a really big number. It's unstable. Remember, on this is an energy diagram, so you can think of enthalpy as energy. It really is a certain type. Remember, on an energy diagram, up high is least stable, and down low is more stable. I'm losing my pen. There we go. Okay. Can heat of formation be negative? Remember, we defined the heats of formation of elements as being 0. I told you there's an exception. Let's just ignore the exception for now. So generally for an element you would think not, but for a compound it definitely can be. So especially compounds. So for this compound, it's -75. And it doesn't mean that it has negative energy. It just means it's more stable, lower than the elements that it's made from. Okay. Here is kind of the definition again. So here is the reaction. Again, this is that definition, the equation that defines it. If I'm interested in CH4, I put these are the reference form elements. And this is the compound that I'm interested in. So reference form elements to make that compound. The heat of this reaction is negative 75 kilojoules. And I'm making 1 mole, so that works. So that's where this number comes from, the heat of formation of CH4 methane. Let's look at that graphically. So here's my energy diagram. Remember, enthalpy is essentially energy, a specific type of energy, stored heat. And here I have these are my reference forms. And in this case, if I look for the CH4, it's down here. It's got a negative number because it's more stable than the elements that made it. And I see I'm going to have something over here. Let's erase that. Okay, enthalpy content is relative to the chosen reference form. The reference form is defined just so that we have something to compare with. Okay, well, the handy thing about heats of formation is that you can use these to determine the heat of a reaction. Wow, so heat of reaction. And so what we're going to do is just compare how much energy is in the reactants versus the products. So again, heats of formation have this fancy definition, but it's easy to just think of it as this is how much enthalpy is stored in that substance. So I'm comparing nitrogen gas and oxygen gas and so on. Notice, you guys, I didn't write nitrogen N2. And, you know, that doesn't matter. I chose an unstable state to make this math easy, basically. But if this were N2 gas, this number would be 0 because that would be the reference form. But I did not, so I've got a number here. This is less stable. Okay, anyway, let's look at how this affects a reaction. So another diagram. What I can do is I can add up the energy or heats of formation of the reactants. They're up here. And then I've got my energy present in the product. And I can see the difference. I see this is an exothermic reaction. And to get my heat of this reaction, given up here in the purple, I'm just going to compare these two. I'll do final minus initial. Okay, so oversimplified, heat of reaction is the difference in products and reactants energy. The extra thing there. And for energy, we're talking about heats of formation. So the standard enthalpy of a reaction, standard just means we're at 1 atmosphere and 25 C, because that does change the energy in a substance. But anyway, you know that standard enthalpy of a reaction, we call that the heat of reaction. And okay, and that's what all that is. So how do we get that? We compare reactants and products. And usually it's a little bit more complicated than the one we just did, because we may have more than one reactant and product, and also the coefficients may not all be 1. So the N here is the coefficients from the chemical equation. So I'm adding up the products and subtracting the heats of formation of the reactants. And so N is coefficients. I'll show you one more slide. This one's kind of long, isn't it? Before we do this practice. Just so you know, heats of combustion, they are the amount of, they are the heat of formation, I'm sorry, they are the heat of reaction for combustion, for burning something. The thing is that sometimes they're listed in as positive numbers, even though these are exothermic reactions. So be aware of that. Of course, you should recognize that this is combustion because I'm adding oxygen and I'm getting these two products. That is, we've learned that before, that that's what combustion looks like. It is exothermic for sure, but on a table or something, you may see it listed as a positive number. So just be aware that it is assumed to be the amount released. And you guys, that's not consistent. Some books will list it as a negative number. So just know that it is that. And the other thing is, when we start calculating these, we'll also be doing some other kinds of reactions, like these are just physical reactions. Know that when we say heat of fusion, fusion means melting. And heat of vaporization, you know, the symbols for those. Because if I ask you to determine the heat of vaporization of something, you need to know that that means making it go from a liquid to a gas. Okay, let's look at some examples.